The electric universe. A subject of growing interest on the internet and of much confusion as well. If you've recently come to this subject, you may have heard more from debunkers than from those truly familiar with the work. That's just the nature of popular science forums on the internet today. In this interview with Australian physicist Wallace Thornhill, we begin the task of correcting the most common misconceptions. Our hope is that you will take this opportunity to compare the words of the critics to the actual hypothesis as formulated over several decades.
The greatest challenges facing newcomers to the electric universe is to have some guide to where to start and the basic principles behind the electric universe. We have, of course, suffered these violent knee-jerk reactions from the mainstream, and of course they tend to be the things that people look for when they first come to the electric universe. They want to know, what do the experts think? And that poses a bit of a problem because generally it's not a dialogue between us and the experts, so to speak, but it's more in the nature of bald statements of fact. You know, Newton's laws are sacrosanct, and anyone who questions them is wrong. The same goes for Einstein's theories of relativity. Anyone who questions those, you just don't give them the time of day. But of course, if we're ever going to progress, then science must address questions raised by so-called outsiders, because often insiders are don't have the courage to actually ask these questions because they know what the automatic response will be. The idea that the electric universe is some recent crank theory that's been put forward and has gained a following is not correct. The term the electric universe is a history going back many decades, and it's been used by some top scientists. One of those, of course, was Hans Alfvén, who spoke or had articles published under the banner of Alfvén's electric universe. So it is an idea which actually had currency in the last century, in the 19th century. And for those who care to go back into history and look at the major scientific journals of that period, you'll notice that articles on the electrical nature of comets and the possible electrical activity on the sun were topics of discussion. Unfortunately, in the early part of the 20th century, all of that was more or less suppressed, is probably the best way to put it, because it became or physics and the study of our environment in space became more the study of theoretical physics, mathematical physics, and the suggestions of the past were lost in this rush to try and explain things in mathematical terms. Something that, of course, we're brought up to believe, and that is that gravity is the controlling influence in the universe. It's what causes the planets to orbit around the sun and the moon around the earth, and to cause the tides upon the earth. All of that is true up to a point, but the thing to remember is that basically there is no understanding of gravity. Newton was wise enough not to propose any theory. He just said that here's an equation, my law of gravity, if you like, and it works, but I make no hypotheses. Unfortunately, those who came later were prepared to follow Newton's path and feel that they had explained gravity, when in fact they hadn't. Einstein's theory doesn't explain gravity. It has matter somehow affecting space in a way which is completely unphysical, in other words, warping empty space. There's no explanation as to how this might happen or what it even means. So we have more equations but without any real meaning. So I don't argue with the fact that gravity is the controlling factor in the solar system and that it does raise tides. However, what I'm suggesting is that we don't have an explanation for gravity, and until we do, we will not understand the limitations of that theory. One of the limitations is, of course, that there is this peculiar constant called big G, the constant of gravitation. Now that's measured on Earth, and it's the least well-established constant in physics. It varies every time they try and measure it, and yet it's applied as a universal constant throughout space. And this is just a pure assumption. And the fact that it varies on Earth should be a signal that something is going on that we don't understand. And until we understand that, then we should allow the possibility that gravity is itself a secondary force in the universe. It's a very weak force, and that's one of the puzzles. It is so weak that we can actually jump into the air away from the entire pull of the planet Earth. So there is this difficulty in trying to explain it in terms of the other forces because they're all so much stronger. But the electric universe just takes the simple proposition that it is an electrical force. It's a very weak leftover force because although all matter is made up of positive and negative particles, they don't always balance exactly, particularly in space because they're orbiting systems, and therefore at any one moment the charge is not balanced. So taking that very simple proposition and suggesting that electricity plays a part opens up all kinds of new possibilities, and some of those include being able to explain what's going on in the centres of galaxies, because the energy involved there is enormous. It appears to have a very powerful gravitational pull. We know that galaxies don't rotate as expected. We have to invent dark matter and add it just in the right places to save the appearances, so this is one problem. Another one is the enormous bursts of energy from very small volumes of space which are attributed to black holes. And because a black hole is a purely mathematical entity, that should raise questions too as to our understanding of what's going on in terms of Newton's law. The idea that there is no evidence for electrical activity in space, either within the solar system or outside the solar system in deep space, is quite incorrect. One of the key signatures of an electric current is the magnetic field that it generates. And once we got spacecraft outside the Earth's environment into space, what we found was that it's threaded with magnetic effects. And when radio astronomers looked at objects in deep space, the thing that they discovered, and which was unexpected, is that they were receiving radio signals which showed that there were magnetic fields threading galaxies, and also associated with stars and stellar birth and so on. So these magnetic fields are the signature of electrical activity in space. Unfortunately, there was a notion that gained currency in the early days of space exploration, and that is that plasma, that's the all-pervading thin material in space, was a superconductor. Now, it is true that it is an extremely good conductor. However, in space it is unable to carry much current because there are so few particles to carry that current, so the density is too low. And also the fact that the plasma is radiating radio signals shows that it is losing energy, and therefore it is not a superconductor. It cannot maintain the magnetic field without electric power being supplied. So from these points of view, simple points of view, we have plenty of evidence of electric currents in space. When I was at university, I recall the lecturer calculating how much energy would be required to separate all of the electrons from all of the charged nuclei in a teaspoon of salt. And of course the figure was phenomenal. and so it was generally regarded by everyone that that was problem solved. You can't separate charge, it requires too much energy. And of course this was also transferred to plasma in space. However, plasma physicists themselves know that all you need to do is have regions of plasma moving past one another, and they will induce electric currents in each other. So you don't require bulk charge separation. This is the false argument. You're not separating all of the electrons to one side and all of the protons to the other. What you're doing is leaving them as a mixture, but with slight offsets or slight differences in their numbers. And that's all that's required to allow for an electric current to flow in plasma. It is obvious that charge separation does exist simply by fact of the electric currents that are detected by radio astronomers, and also by the very cataclysmic events we see in deep space, like supernovae explosions and so on, which can be actually characterized as a sudden coming together of separated charge. This can happen, according to Hans Alfvén, across what's called a double layer in plasma, where charge is separated. This is one of the areas where charge is physically separated in space. And Hans Alfvén was of the opinion that these charge-separated layers, or double layers as they're called, should be classified as discrete celestial objects, because they emit radio noise, they can accelerate particles, cosmic rays and so on, and they can explode, as sometimes happens near a star, to give those spectacular results. Hans Alfvén, who was the father of plasma physics, received the Nobel Prize for his early work, and he put his reputation on the line by actually admonishing astrophysicists for their misuse of his work, because he felt that he had made a fundamental error in his initial work by ignoring the electric currents that must be involved in producing the magnetic fields that are witnessed in space. In fact, he went on to actually chart a circuit diagram for the Sun. So he said that astrophysics was heading for a crisis. Now, he said that back in, I think it was 1970, and yet that crisis still hasn't managed to come about, because astrophysicists have been able to successfully ignore his admonition, which I feel has been at great cost, both in time, money and effort by our space probes and generally in science.